So now we're going to talk about exponential and logarithmic models. Basically story problems. Now I really don't think these are too bad. People always get intimidated by story problems, and I just I honestly personally don't understand why people get so intimidated. You just gotta take your time, read through it, and write down your information, and usually it's pretty straightforward in my opinion. But let's go ahead and see what we have here. So let's talk about population growth. And population growth is modeled by f of x is equal to, whoops, a natural exponent to the bt. Now, one thing that we could look at if we're thinking about the graph of this, so I'm just going to sketch a rough thing of the graph here, and we know we have a y-intercept here, and then this b, I'm just going to draw one exponential curve here. This b is going to have effect on how fast this thing grows. Like how fast, I did two kind of here, one with a dotted line, one without the dotted. So that's what b is going to affect. And then this here, a, is my y-intercept here. So one thing you want to think of, especially if you're dealing with population, a is often referred to as the initial population. So let's look at a problem here dealing with this. And we're going to look at this as dealing with bacteria growth. So what we have here is the number of bacteria is increasing exponentially. And the reason we're saying we have that sentence here where it's increasing exponentially is it could be, it's not necessarily guaranteed that it would be. It could be increasing linearly, which would be a straight line. And so you have to know, just because we're modeling bacteria doesn't mean it's an exponential function. So we have to know that it's an exponential growth here. So it's increasing exponentially. So after 3 hours, there are 100 bacteria, and after 5 hours, there are 400 bacteria. So we're going to do two parts here. Write a model for bacteria growth, and then B, how many bacteria after 6 hours. So again, my bacteria, or my exponential growth I should say, is f of x is equal to a e to the bx. Well, let's not do x in this case. Let's go ahead and change this because we're talking about time. So let's do t for time, bt. Now I am going to make a note here. T is going to be in hours. Now, because we could make t in any units, I could have made t days, but we should specify it. And of course, it makes sense that I'm making it hours because I'm given hours as far as information in the problem. I've got 3 hours and then 5 hours. All right, so, and then let's just go ahead and write down f at t. This is the number of bacteria after T hours. Alright, so let's look at this then. I have to figure out what A and B are. Well, I've got 2 points that they've given me. I know that when T is equal to 3, F at T equals 100. And then when T is equal to 5, F at T equals 400. So what are we going to do? Well, we're simply going to substitute that in here. So we've got here 100 is equal to A E to the 100. Oops, not 100. Hello, let's plug in the right number. T is 3. So 3B. And then we also have 400 is equal to A E to the 5B. Now, we have 2 equations and 2 unknowns, so there should be a way to solve them. And this is what gets people... Whoops, I don't know why I did that by accident. But what gets people about this with these 2 equations and 2 unknowns is this is typically not one that you've seen ever before on how to solve them. Now, it turns out there is kind of a strategy to do this, and it's basically divide the 2 equations. So I'm going to have 400 is equal to A e to the 5b divided by 100 equals A e to the 3b. And, well, 400 divided by 100 is easy. That's just 4. But notice I have A divided by A, which is just 1. So I'd have E. Now, what do you do to exponents here? 5b over e to the 3b, we subtract them, and so this would be e to the 2b. Now I've got a single equation, and it's an exponential equation, but we know how to solve this. I would do the natural log of both sides, and so you'd have the natural log of 4 is equal to 2b, and so b is equal to the natural log of 4 over 2. And now that's the exact answer, but since we're trying to create a model, let's go ahead and get a decimal answer for that. So natural log of 4 divided by 2, and you get that this is approximately 0.6931 for b. Alright, well I now still need to figure out what a is, but I now know what b is, so really that shouldn't be too difficult. I should be able to use either one of these equations. For instance, 100 is equal to a e. I now know what b is, so it would be 3 times, because it's been 3 hours still, 3 times 0.6931. And then a is equal to 100 divided by e to the 3 times 0.6931. So again, we'll write this as a decimal answer. So let's go ahead and do this. And I'm just going to round this to 1 decimal spot, approximately 12.5. So then for part A, my model is f at t is equal to 12.5 e to the 0.6931 t. Now part B is actually pretty straightforward, because part B now is just, well, hey, you have your model, evaluate this for 6 hours. So that's just f at 6, which is 12.5 e to the 0.6931 times 6. And then, of course, we just do that arithmetic. And so let's see here, 12.5 e to the 6 times 0.06931. And it helps if I do this correctly. Sorry here, let me pause it and get some calculator errors. Alright, now I got this, and so if I get this as approximate answer, this is 799.77, which I would just round to approximately 800 bacteria. Alright, so let's look at another problem or two dealing with applications of this. And this one here, I'm going to do a logarithmic application here. So this is talking about pH levels. Now, if you've taken chemistry, you've probably talk about pH levels. If you haven't taken chemistry yet, you will talk about them. And just to kind of give you a rough idea here, a pH, if you're measuring the pH of a substance and you get 7, this is what's called neutral. And then if the pH is less than 7, it's acidic, or it's an acid. And if the pH is greater than 7, it's a base. And so, like for instance, lemon juice is an acid. It has a pH less than 7. Hydrogen peroxide, which you might have put on a cup before, is a base. It's got a pH bigger than 7. All right. So, but where does these numbers come from? Well, there is a formula for the pH. The formula for computing the pH of something is that the pH is equal to the negative common log of the hydrogen ion concentration. So, let's look at two quick examples here with this. So, let's see here. Let's do it the pH when H plus is equal to 2.3 times 10 to the negative fifth. And so the pH would just be simply, this is literally just equation plug and chug, minus log of 2.3 times 10 to the negative fifth. And so let's go ahead and plug that into our calculator. And we get that the pH is 4.64 approximately, just rounded it to 2 decimal points. Now, we could also go the other way. We could compute the pH, not compute pH, compute the hydrogen ion concentration when the pH is, let's say, I don't know, 4.1. Okay, well if we do that, we would have 4.1 equals negative log of the hydrogen ion concentration, which would be negative 4.1 is equal to the log of the hydrogen ion concentration, which then we would have 10 to the negative 4.1, because we're doing common log, is equal to your hydrogen ion concentration. And then we could, of course, approximate what this is. And if you approximate this, you would get, just 1 second, I have my calculator in a weird mode. You'd get 7.9 times 10 to the negative fifth power for a pH of 4.1, which makes sense because it's somewhat close to what we had when we had a pH of 4.64. And you can see the one thing you can see actually here is that the lower the pH, the higher the hydrogen ion concentration. Okay, so we could look at one more example here, I suppose. And this one's one that I kind of like just because it deals with electrical engineering a little bit. And this is with decibels and the intensity of sound. Now, this is something you've probably seen before, like decibel. Like if some stereos, some things have decibel readings on it. So what we're going to do here is go ahead and define it. We have an equation, and the equation here is given by, well, they use beta, and it's given by 10 log of I over I0. And I0 is kind of, well, it's a constant. It's equal to 10 to the negative 12, which this is roughly the faintest sound you can hear. And as a side note, the units for these are watts per meter squared. So watts is a unit of power, and then meter squared is just saying what's the intensity of a power in a particular area. Sorry about that. I accidentally hit the power button on my tablet here. Alright, so let's look at here. So let's see what the decibels are for what is considered the threshold of pain. Now that's subjective, but this is basically, does it hurt your ears? And the threshold of pain has I is equal to 10 to the 0 power, which of course is just 1, but I'm going to leave it as 10 to the 0 because we're going to compute a decibel here. So this is beta is equal to 10. This would be log of 10 to the 0 over 10 to the minus 12. Now, the reason I'm doing this is I can do this whole problem without even a calculator. This would be 10 log of, well, subtracting exponent 0 minus negative 12 would be 10 to the 12th power. And then, since this is the common log, this is base 10, so it's saying what exponent do I put on 10 in order to get 10 to the 12th? Well, of course, you just have 12. So this would be 10 times 12, which would be 120 decibels, which is a very loud sound. Now, something that's even louder than that would be a jet engine if you were standing only 30 meters away from it, which is actually pretty loud as well. So it's even louder than this. I believe it would be, I think it's 12,000 decibels is what it would be. But I'd have to double check the computation. So for if you're, and of course 30 meters squared, I mean you're talking standing basically, or 30 meters from a jet engine, you're talking basically roughly a football field length, standing from a, not even a football field, I'm sorry, like standing on 30-yard line, and the end zone would be like roughly how close to the engine you would be standing, and so of course it would be very loud. Alright, but you know, there's tons of applications. I can't do example problems of all of them, but there are a lot of, as I say, kind of real-world examples. Another one that you could look, a lot of textbooks have, is if you want to know what mortgage you would have to pay as far as a monthly payment on a mortgage. That's dealing with an exponential equation. So there's a lot of things that these are useful for. But we're going to move on to some new topics after this, now that we're done with exponential functions and the logarithms and solving equations.